Number 12. The abyss itself is where the sea stops behaving like a place and starts behaving like an enemy. The ship slips past the edge of the world before you have time to understand what changed. Below the hull, the ocean stops behaving like water and starts feeling like a wall. Black, silent, immeasurably deep. At Challenger Deep, the pressure climbs to about 1,000 times what you feel at sea level, enough to turn the idea of down into something almost abstract. Yet this is not empty space. In 1875, HMS Challenger took a sounding here and found a drop so extreme it rewrote ocean science. More than a century later, James Cameron descended alone into that same abyss and came back with proof that a human can enter the deepest known point on Earth and survive. The deepest thing in the sea still hangs in the dark below. Food, mates, or our imagination? On March 23, 1875, the British survey ship HMS Challenger lowered a line southwest of the Mariana Islands and waited for the bottom. The crew expected deep water. They did not expect a number that would force the maps to change. The line kept running out. The sea kept taking it. When the sounding finally came back, it pointed to a trench far deeper than anyone had measured before. That first reading was crude by modern standards, but it was enough to make the place matter. Challenger Deep entered the record as a limit. Not a coastline, not an island, a limit. By modern measurement, the deepest point comes out to about 10,994 meters, or 36,069 feet. Most people call it about 11 kilometers down, 7 miles. Those numbers sound tidy until you try to picture them. 7 miles is a long walk on land. In the sea, it is a vertical collapse into a world with no sunlight and almost no room for error. The Hadal Zone begins at 6,000 meters. Challenger Deep sits far below that line. NOAA treats it as its own kind of place, with its own ecology, not a blank hole in the planet. That is the first unsettling fact. The second is simpler. Life still gets down there. In 2009, the Mariana Trench became a marine national monument. By then, it had already become something else in the public mind. A place for records, a place for machines, a place where men and women built hulls thick enough to survive what the ocean is doing to them every second. The trench had never stopped being mysterious, but now it had become measurable. On March 26, 2012, James Cameron completed a solo dive to Challenger Deep in the Deep Sea Challenger. He reached the bottom alone. He stayed long enough to prove the impossible had become engineering. Then he came back up through the same crushing dark. You can almost make the descent feel quiet until you remember what pressure means. About 1,100 atmospheres down there, roughly 1,000 times sea level pressure. Every surface is hostile. Every seam matters. Every decision is made before the dive begins, because once you are in the trench, there is no casual correction, no easy repair, no sudden rescue. You are inside a place that does not forgive. You are also inside a place that still resists certainty. Even now, the exact deepest point shifts across surveys. Challenger Deep is accepted as the bottom, but the precise maximum depth can move with better instruments and new readings. The abyss is real. Its exact shape is still being argued over. Then there is the contamination, the part nobody wanted the trench to teach. In 2018, researchers reported plastic fibers in 100% of amphipod samples from the Mariana Trench. Not near the surface, not close to shore. Here, in the deepest wild place humans could reach. The trench is so remote it feels like the kind of place that should have escaped us. It did not. Even here, human debris finds a way down. Even here, the dark is not untouched. Picture the scene from the sub. The viewport is a small circle in a pressure shell. Outside it, there is nothing you can use to orient yourself. No horizon, no bright blue fade. Just black water packed so tightly it behaves less like water and more like force. You are looking into a world where the visible distance is measured in inches, not miles. Any light is swallowed almost immediately. Any sound is reduced to the hum of your own machine. If something moved out there, you would not see it coming in the way the surface creatures do. You would get only a glimpse, a shape, a suggestion. Then darkness again. The Mariana Trench matters because it strips away the easy story. It is not a monster in a fairy tale. It is a place where the sea stops acting like scenery and starts acting like a test. It tests hulls. It tests instruments. It tests the body. It tests how much mystery a human mind can tolerate before it starts filling the dark with its own inventions. And the trench still wins most of those arguments. The maps keep improving. The measurements keep tightening. The dives keep getting better. But the feeling remains the same. Down here, the ocean is not simply deep. It is absolute. The last thing you see before the frame goes dark is a single fading point in the void. And it looks less like an ending than a warning. Number 11. The misunderstood collapse. Start with the photo. A pale head, a sagging mouth, skin that looks like it forgot how to hold itself together. When the blobfish first went viral, people treated it like a punchline from the deep. The image seemed to prove that the ocean, at its worst, could still produce something almost cartoonishly wrong. But the real animal is Cycrolutes marcetus, and it lives off Australia and nearby New Zealand at roughly 600 to 1,200 meters. Down there, pressure is not a background condition. It is the main fact. A body at that depth has to survive under forces that would crush the neat, familiar shape of a shallow water fish. So this one did something clever. It became soft, low density, light for its size. It lost the swim bladder that so many fish use to control buoyancy, because a gas-filled sac is a liability when the water itself is pressing in like a vice. Its maximum length is only about 30 centimeters. Small body, big problem. Or rather, a problem that only looks big if you are standing in the wrong place. Underwater, the blobfish does not look like the internet version. It looks closer to a blunt-headed bottom fish, pale and plain, sitting where it belongs. The meme face comes later. That is the trick. Not in the trench, not in its own world, but on deck. In the wrong air, with the wrong weight on its tissues. Haul one up too fast and the pressure drops. The body collapses. Soft tissue spreads. The head seems to melt. The skin sags into a shape that looks invented by a cruel cartoonist. What people remember is the collapse, not the animal. The species was described in 1926 by McCullough, long before the internet decided it was ugly. That matters because the joke came after the science. Decades later, a related species, Cycrolutes microporos, became the face everyone recognized from a 2003 image that spread through news and email and every corner of the early web that liked a strange animal story. That photo was powerful because it looked like proof. Proof of deep-sea absurdity. Proof that nature had gone too far. It was neither. It was a body in distress. The numbers line up against the myth. A female can carry as many as 100,000 eggs. That is not the signature of a failed creature. That is the signature of one that has to gamble on survival in a place where very little gets easy. The deep sea does not reward charm. It rewards what works. A soft body can work there. A lack of a swim bladder can work there. Looking like a joke only happens when humans drag the fish into the wrong physics and call the result its real face. By 2013, the blobfish had been named the world's ugliest animal in an Ugly Animal Preservation Society poll. A perfect human move, really. Take a species that lives in a world almost nobody can visit, flatten it into one bad surface image, and vote on its appearance like it had ever agreed to be judged there. The official portrait and the real animal do not match. One is a decompressed casualty. The other is a deep-sea survivor built for 600 to 1,200 meters of pressure, silence, and darkness. The official story says ugly. The real thing says adaptation. Number 10. The oxygen zone ghost. Lives where even predators hesitate to breathe. In 1903, Carl Chun described it from the dark water and gave it a name that sounded like a warning. Vampiroteuthis infernalis, the vampire squid. The title did most of the damage. It made the animal sound like a monster before anyone had really looked at what it was. Chun first misread it as an octopus. That is easy to understand now. The body carries a cloak-like membrane. The arms spread in a way that looks wrong for a squid. The whole animal seems assembled from parts that should not belong together. In old museum jars and early drawings, that strangeness did what human imagination always does in the dark. It filled in the missing pieces with fear. But the first clue is not the shape, it is the address. This animal lives in the oxygen minimum zone, often around 600 to 800 meters down, Sometimes deeper in the broader 2,000 to 3,000 foot range, NOAA uses for its deep water habitat. That is the part of the sea where oxygen drops so low that many predators simply do not follow. The vampire squid does not dominate that world. It slips into the gap left behind. A place too thin on oxygen for the fast hunters becomes a refuge for something that does not need to rush. That is the break with the myth. It is not a terror that charges through the dark. It conserves energy. It drifts. It waits. It lives in near darkness and spends almost nothing it does not have to spend. The body is built for that economy. The cloak-like web can fold and flare. The defensive displays can flash red and pulse in the black water. They look like a horror prop from a better-funded nightmare. But they are not proof of aggression. They are proof of survival. The food tells the same story. A 2012 Nature summary described feeding behavior that was almost the opposite of a hunter's attack. The animal uses two retractile filaments to collect drifting material, marine snow. Bits of life falling through the water column, the leftovers of the sea, not a chase scene. It gathers what passes by. That is how a small cephalopod makes a living where energy is scarce and waste becomes dinner. And the lineage is just as strange. Vampire squid is the sole living member of its own order, Vampiromorphidae, one of a kind. Not a weird squid that failed to become something else, a separate branch, a survivor of its own design. The horror gets stranger when reproduction enters the picture. A 2015 study found multiple reproductive cycles, not one final sacrifice and collapse. Popular coverage pushed that into a much bigger number, more than 100 spawning events. Even there, the animal refuses the dramatic script people want from deep-sea creatures. It does not behave like a single-use machine. It keeps going. There is still one detail nobody has fully pinned down. Exact wild lifespan remains unresolved. Even with the reproduction work, the clock is not fully read. The deep keeps that secret to itself. So the name vampire stays, but only as an echo. It clings because it works in headlines, and because the cloak and glowing displays make a better monster than a drifting specialist ever could. Yet the evidence keeps bending the other way. A body first described in 1903, a habitat where many predators cannot breathe, a feeder that takes what falls, a lineage with no living twin. The thing that looks like a curse is actually a solution. In the black water, that solution is tinged by silence. Number 9. The baited mouth. The next creature is not about strength, but about surviving where almost nothing can afford to move. Deep below the surface, black water turns into a hunting ground with no grass, no coral, no cover. Just emptiness. In that emptiness, a female anglerfish waits with a light hanging above her mouth like a tiny, stolen moon. The first thing a small fish sees is the glow. It does not see the jaws below it. It does not see the mouth that opens wider than the body should allow. It sees a promise. A point of brightness in a world that has none. Then it drifts closer. By the time the fish understands what it has done, the trap has already closed. Female anglerfish use that glowing lure to pull prey into range in black water. In some species, the lure dangles from a stalk like a worm, or pulses like a baited signal. The details vary. The effect does not. Small fish approach the light and are swallowed by an ambush-built jaw. In the deep sea, where food is rare and distance is everything, even a few centimeters can decide whether something lives long enough to matter. There are 162 known species of deep-sea anglerfishes. That number alone tells you this is not one odd monster. It is a whole family of solutions, different bodies, different lures, different depths. One recent summary described a bioluminescent lure at about 3,000 feet below the surface. Another rare mating video came from 2,600 feet down in the North Atlantic. That is the world this fish belongs to, a place where a flash can be a meal, or a message, or both. Then the story gets stranger, because the lure is only half the horror. The female black sea devil, Melanocetus johnsonii, can grow to about 18 centimeters. The male can be 2.9 centimeters. That is not a typo. In some species, the female is about 10 times larger than the male. He is not built to fight. He is built to find. His life is a search problem in near total darkness, with almost nothing to guide him except chemistry, chance, and whatever signal the species has left in the water. So when he finds her, he bites. Not a quick bite, a permanent one. In some deep-sea anglerfish, the male bites onto a female and eventually fuses with her tissues. His body changes. Major functions drop away. In some species, he becomes, for all practical purposes, a living reproductive appendage, a permanent sperm source attached to the female's body. The ocean is so empty that separation is not an option. Proximity becomes the whole system. That is the part people remember when they hear about anglerfish sex. It is brutal enough on its own. But the twist is what evolution may have done with the lure before that. A recent study of 13 anglerfish genomes suggested that immune system reduction helped make this bizarre mating strategy possible. The female does not reject the male the way a body normally would. The barrier softens. The biology gives way. Once that happens, the same glowing lure that once pulled in prey may also have become a signal for finding mates in total darkness. What began as a trap may have doubled as a lighthouse. If that sounds impossible, look at the timeline. Some studies place the origin of glowing lures in certain deep-sea anglerfish between 23 million and 34 million years ago. That is long enough for darkness to shape a body in more than one direction. Not just feeding, not just hunting. Finding, holding, remaining visible in a place where visibility itself is almost gone. This is where the animal stops looking like a fish and starts looking like an argument with the deep sea. A lantern on the end of a stalk. A mouth that can vanish a victim in one snap. A male so small he seems like a missing piece. A female carrying the body of her mate as part of her own. It is elegant in the way all extreme survival systems are elegant. It is also the kind of thing that makes a person look twice at a dark aquarium and decide not to stand too close. You can see why sailors, filmmakers, and biologists all keep reaching for the same words. Strange, alien, mythic. But none of those words are quite enough. This is an animal that uses light to exploit hunger and isolation at the same time. It lives where food is rare, where mates are rarer, and where the gap between finding and failing can be measured in one flicker. Imagine the male coming in through that blackness, small enough to miss, desperate enough to commit, and the female waiting with her lure still glowing above a mouth built for one clean ending. The dark does not just hide the anglerfish, it works for it. Number 8. The rumor that became a body. Began as a sailor's nightmare and ended in a camera frame. In the 1800s, men at sea saw arms in the water, torn netting, and enough broken debris to turn fragments into a story. They called it a monster because they had no better word. Kraken, devilfish, sea serpent. The shape changed from harbor to harbor, but the fear stayed the same. Then the bodies started turning up. Stranded carcasses, beaks found in whale stomachs, sucker marks on whale skin. Pieces, not proof. Clues, not a living animal. For a long time, that was all science had. A giant squid could be measured after death and imagined before it. It is a strange way to know an animal. It leaves the worst parts of the job to the dead. Tsunemi Kubodera and Kyoichi Mori were working against that silence in 2004. They had sperm whale clues. They had a baited line. They had patience, which in deep-sea work is often the most important tool. Then, in the wild, at last, they photographed a live giant squid. For the first time, the monster had a face that was not made from rumor. The face was not a mythic ship sinker. It was a hunter. Fast. Real. Built for the deep. The giant squid's eyes are reported to reach over 10 inches across. That is not decoration. That is equipment for a world where light has nearly died. Those eyes are adapted for the twilight zone, around 1,000 to 200 meters down, where every dim shape might be food, danger, or both. People like to imagine a giant squid as a brute. The biology says something sharper. It reads the dark. One Smithsonian specimen preserved a juvenile giant squid at 23 feet. Another female on display reached 36 feet. Adults are regularly sighted at 40 feet. That is not a bedtime story. That is a measured animal with a body long enough to disappear into a single black column of water. And even that number is only part of the picture, because most of the animal is still known from fragments. A beak, an arm, a scar, a stomach full of clues. The giant squid's reputation was built partly inside whales. Sperm whales dive where few cameras can follow, and they come back carrying evidence. Giant squid pieces in their stomachs, sucker marks on their skin. The predator and prey rode on each other long before humans could film either one. The ocean kept the body hidden, but it did not keep the violence hidden. Discovery Channel captured the first natural video in 2012. That sounds like a clean ending. It was not. The footage was a breakthrough, yes, but it was also a reminder of how little had changed. Even after the first photos in 2004 and the first video in 2012, most of what people know still comes from dead specimens and museum collections. The animal remains famous for what it was before science could see it clearly. A terror first, a specimen second. The Smithsonian preserved a rare, intact giant squid eyeball after the rest of the body had been scavenged. The eye survived because even in death, the sea goes straight for the softest parts first. A whole creature can vanish and leave behind one perfect organ, sealed in a jar, staring out of a body that is already gone. That is the giant squid story in one scene. A rumor in a sailor's mouth, a carcass on a shore, a camera in black water, a body assembled from leftovers. Even now, the biggest question is still not size. It is identity. Architeuthis dux shows unusually low genetic diversity across a huge range. One species, many hidden lineages. The deep does not always answer the way people expect. It often gives you a body first and the explanation much later. Number 7. The Antarctic heavyweight is the deep-sea giant that forced scientists to freeze the evidence. On February 11, 2007, in the Ross Sea, the crew aboard the New Zealand longliner San Aspiring were hauling Antarctic toothfish gear when the line came up with something they did not expect to keep. A colossal squid had hit a baited toothfish line at about 1,500 meters. It was still tangled in the fishing gear, still real, still enormous. The crew could have treated it like dead cargo. Instead, they stopped. They saved it. They froze the specimen and sent it to the Museum of New Zealand Te Papa Tongarewa in Wellington. That decision turned the animal from a rumor into a body scientists could work on. A whole body, at least as whole as the ocean ever allows. The first numbers were blunt, about 495 kilograms before thawing. Later, after ice loss and thawing, the estimate settled closer to 470 kilograms. The mantle measured 2.5 meters. The total length came out at 4.2 meters. The eyes were reported at 27 centimeters across, 10.6 inches. Each one a dark sphere built to work in water where light is already mostly gone. These are not decorative numbers. They are the shape of a predator that lives where almost nothing can be watched alive. That is what makes the 2007 capture so important. It was not just a dead squid brought in with fishing gear. It was a predation event interrupted by humans. The squid had attacked a toothfish on the line. It had gone after prey in the dark, at depth, in the Ross Sea, and only then got dragged into the human world. That sequence matters. It tells you this was not scavenger debris. It was an active hunter doing what it had evolved to do, until steel, rope, and chance stopped it. The species itself had already been named long before that day. In 1925, scientists formally described the colossal squid. But the description did not mean understanding. For most of the 20th century, the animal lived as fragments. Arms from whale stomachs, pieces in nets, soft tissue too damaged to tell a full story. The 2007 specimen was different because it gave researchers a complete reference point. Not perfect, not untouched, but enough to measure, dissect, and display. Enough to compare the myth to the material. Even then, the specimen fought back against certainty. Freezing changed it. Thawing changed it again. The monster shrank. Early sensational claims pushed the size upward, because that is what happens when a giant animal arrives half frozen and half ruined, and everyone wants the biggest possible answer. But the body itself corrected the story. The numbers came down. The legend had to make room for biology. Officially, it was a display specimen. In reality, it was a damaged body that had already lost part of its shape to the cold. That gap between official and real is the point. A label in a museum can say one thing. The living animal in the Southern Ocean is another. The label can tell you 4.2 meters. It can tell you 470 kilograms. It can tell you where the specimen ended up, frozen and studied in Wellington. It cannot tell you how the animal moved in the dark, how fast it struck, how often it hunted, or how large the biggest wild individuals actually get. The evidence is frozen because the sea did not volunteer a better sample. So the colossal squid stands there in public view as both answer and omission. Big enough to silence a room. Incomplete enough to keep the question alive. A real Antarctic heavyweight. A predator that made scientists preserve the proof before it could turn back into mystery. And the deeper fact is simple. Even now, the known record comes from a tiny sample of damaged bodies. The true upper limit is still out there in the cold, below the fishing line. Number 6. The surface omen. That happened at La Jolla Cove on August 10, 2024. Kayakers saw a dead, short-crested oarfish near the waterline. Snorkelers saw it too. For a moment, the beach went quiet in the way a crowd goes quiet when nobody knows what to call what they are looking at. The fish was huge in the way deep-sea things often are. Long, thin, almost formal. 12.25 feet, 3.735 meters, 74.3 pounds, 33.7 kilograms. A red dorsal crest stretched another 2.17 feet, like a torn ribbon left behind by something colder and darker than the shore. Scientists later identified it as Regalicus russellii, a short-crested oarfish. If you only knew the old stories, this would feel like an omen arriving in daylight. In California folklore, oarfish get treated like messengers, earthquake fish, sea warnings. A thing from below coming up for one last announcement. But the specimen that washed in at La Jolla was not carrying prophecy. It was carrying evidence. On August 16, 2024, scientists from Scripps Institution of Oceanography, California State University Fullerton, and NOAA Fisheries performed a necropsy at the NOAA Fisheries Southwest Fisheries Science Center in La Jolla. They were there to preserve tissue from one of the rarest deep-sea fish humans ever get to inspect closely. The specimen was an adult male. That detail matters because even in death, the animal was still useful. Its tissue could help reconstruct diet, DNA relationships, and ecological niche. Every strand of it was worth saving. And the strange thing about oarfish is where they live. The mesopelagic zone, roughly 200 to 1,000 meters below the surface. Dim water, cold water. A place where you do not so much observe a creature as infer it from the rare occasions it misfires into your world. The 2024 specimen was the 20th documented oarfish wash-up in California since 1901. 20 in more than a century. That is not a trend. That is a handful of accidents spread across generations. So when one appears on a beach, it feels personal. Like the ocean has chosen a single shoreline to speak through. Sit with that scene for a second. You are at the edge of La Jolla Cove. The water is calm. The body is already dead. But it still looks unreal because the shape is wrong for the shore. Too long, too delicate, too deep. It belongs to a place you cannot stand in, only descend through. And now it is here, in the light, where everyone can see the pale curve of the body and the red crest laid flat against sand and foam. That is why oarfish hit people so hard, not because they are monsters, because they are almost never available to the human eye. The deep sea hides them in plain absence. Then one washes up, and suddenly the folklore has to share space with a measuring board. The later necropsy made that split even clearer. The public sees a sea serpent. The lab sees anatomy. The public sees a warning. The lab sees a rare male specimen from a part of the ocean that still resists ordinary study. Both reactions are real, only one is scientific. And the myth is not harmless nonsense. It has teeth in the cultural sense. People remember strange beachings. They connect them to earthquakes, storms, bad luck, change. The fish becomes a symbol because it arrives without explanation. But the real story is harsher in its own quiet way. A deep-water animal surfaced where it should not have been, and by doing so, it became useful to science for a brief, accidental window. There is something almost firelight simple about how the story lands. A body by the shore. People gathered around it. Scientists measuring what the sea gave up. One animal and two meanings. In one version, it is a messenger. In the other, it is a rare deep-sea specimen with tissue samples being preserved because biology still has gaps that can only be filled by chance. And maybe that is why oarfish linger in the public mind. They look like something sent upward on purpose. A silver spine, a red crest, a length that seems too deliberate to be accidental. But the ocean does not need purpose to produce mystery. It only needs depth, pressure, and the occasional mistake. By the time the La Jolla fish reached the lab, the beach version of the story was already fading. The tide had moved on. The crowd had thinned. What remained was the specimen, the measurements, the preserved tissue, and the old unease that comes from seeing a creature from the lower dark laid out under clean lights. Long after the crowd leaves, the image stays. A thin, silver body on the sand, red crest folded down, the shore holding still around it. Number 5. The false jellyfish. Start with the number that should make you pause. 10 meters, 30 feet. That is the average length of the tentacles on a Portuguese man-o-war. NOAA puts the maximum at about 30 meters, nearly 100 feet. National Geographic pushes that higher, to 165 feet. Either way, the point is the same. The visible blue float is only the flag. The weapon is what hangs below it. A sailor sees it first as shape, not threat. A translucent sail. A little blue bladder lifting out of the waterline. Pretty, almost fragile. Then the tentacles register. Long strands drift loose in the swell, riding the surface like fishing line nobody can see. That is the Portuguese man-o-war, Physalia physalis. Not a true jellyfish, a siphonophore colony. One animal in the way a ship is one thing, even when the parts do different jobs. NOAA describes the colony as built from specialized, genetically identical zooids. 4 main parts. One floats, one feeds, one captures prey, one reproduces. The float can rise up to 6 inches above the waterline, like a tiny warship under full sail. It is not decoration, it is movement. Wind and current grab that gas-filled body and push the colony across the sea, while the tentacles drag below, waiting. That is the trick. The part that looks least dangerous is the part that moves the whole body. The sail catches the wind. The tentacles do the work. It can travel in groups of 1,000 or more, scattered by current, gathered by weather, turned into a drifting field of stings. A beach looks calm until the next set of waves brings them in together. The sting is not a warning tap. The tentacles carry venom-filled nematocysts that can paralyze fish and deliver a vicious sting to people. Those cells fire on contact. No bite, no bite mark, just touch, and the machinery goes off. The pain can be immediate and severe, with lines of welts that trace the path of the tentacle across skin like a live wire had been dragged there. What makes this creature so efficient is that nothing about it has to look efficient. From a distance, it can look elegant, even delicate. The float catches light. The blue tint blends into the surface glare. The tentacles vanish until they do not. And then the body you thought you were looking at is only the visible tip of a much larger danger. The numbers keep getting worse the closer you get. 6 inches above the water, 30 feet below, and often more. Up to 100 feet in NOAA's account. Up to 165 in National Geographic. That spread alone tells you how hard these animals are to measure in the wild. They are not laid out on a table. They are moving, stretching, contracting, breaking apart in surf. A specimen that seems modest one moment can turn into a much larger problem the next. NOAA says a Portuguese man-o-war can still sting weeks after washing ashore. Dead on the beach, dried by sun and salt, it remains dangerous. That is an ugly detail, because it means the threat is not tied to life in the simple way people expect. A washed-up colony is still a trap, a child running barefoot, a hand lifting debris, a curious tourist picking up the blue float because it looks like a toy. The contact can still trigger the sting. This is where the name gets under your skin. Portuguese man-o-war sounds like a single animal with a single body. It sounds like a thing that should be easy to understand. But the colony works like a small city built for one purpose: drift, hunt, survive, spread. Each zooid is specialized. Each one is part of a machine that presents as one soft, shining thing on the surface. That is what makes it so effective and so deceptive. There is a reason it keeps showing up in stories about dangerous seas. It lives where people think they can see everything. Right at the top, right in the sunlight. No trench, no abyss, no black water. And still it hides its force in plain sight. The ocean does not always need darkness to be terrifying. Sometimes it just needs a blue blur and a thread you did not notice until it was too late. A beachgoer sees the float first. A sailor sees the cluster. A biologist sees the colony structure. A sting victim remembers the speed. The sea does not announce the strike. It lets the float drift, lets the wind carry it, lets the tentacles trail like nothing at all, and waits for skin to make the mistake. One colony, 4 jobs. Tentacles that can stretch to 30 meters, sometimes 100 feet, sometimes more in major references. A float that can rise 6 inches above the waterline. Stings that can paralyze fish. Pain that reaches people. Even after death, even after the surf throws it onto the sand, the warning is still active.
Number 4. The reptile that returned to the sea. The old story is simple. Snakes belong on land. The sea belongs to fish, sharks, and things that never needed lungs in the first place. But the animal does not care about the story. It crossed that line anyway. Sea snake sounds like one creature. It is not. True sea snakes include 64 recognized species, and they are fully marine. A related group, the sea kraits, still come ashore to lay eggs. 8 species belong in that second camp. Same water, different life plan. Look at the body, and the argument gets harder to ignore. Paddle-shaped tails, nostril valves, salt-excreting glands, a shape built for water, not borrowed from it. And still, they breathe air. They have to surface. They do not have gills. That detail changes everything. This is not a reptile that vanished into the deep and forgot its past. It is a reptile that keeps returning to the surface because evolution stopped halfway and then kept going in a new direction. They live in tropical waters across the Indian Ocean and the Eastern Pacific. Reefs, seagrass beds, muddy bottoms, places with cover, places with prey, places where a thin, silent hunter can disappear in a second. The yellow-bellied sea snake goes further. It can drift far offshore and feed near the surface. A snake that does not need land for months at a time. A reptile riding open water like it was built for it. The numbers get stranger the longer you stay with them. One Smithsonian summary says the yellow-bellied sea snake can go 6 to 7 months without fresh water. It is about 80% body water. In the dry season, some individuals lost up to 18% of body mass. That is a brutal margin. The body is holding itself together while the ocean keeps taking. The danger is real, but it is usually not the drama people imagine. Sea snakes are venomous, not poisonous. The problem is fangs and handling. Most bites happen when fishers pull them up tangled in nets. That is the moment the animal goes from hidden to frantic. A quiet hunter becomes a defensive one in a human hand. The myth says the most dangerous sea snake is the one with the strongest venom, full stop. The record was never that neat. The Natural History Museum notes that a popular older claim was wrong. The name most often carried around by the public did not survive the check. Dubois' sea snake is now considered more potent among sea snakes. The legend was cleaner than the science. The science was smaller, messier, and better. Start with the family tree, and the whole thing shifts. These are not just ocean snakes. That phrase hides the split. True sea snakes are fully marine. Sea kraits still come back to land. One group has cut the cord. The other still remembers the shore. That difference decides where they rest, where they breed, and how much of their life is spent one breath away from drowning. There is another number that matters. In a 2009 assessment, 10% of sea snake species were already at elevated extinction risk. Not a rumor, a count. A warning sitting inside the official record. The Australian Institute of Marine Science also points to bycatch as a major concern, especially in places like the Great Barrier Reef, Western Australia, and New Caledonia. The broader cause is still not fully understood. The losses are real. The mechanism is not always obvious. That is the unnerving part. The animal looks complete. Tail, glands, valves, venom, all of it tuned for marine life. But its survival still depends on details humans can break without meaning to. Net by net. Reef by reef. And then there is the body itself. Long, narrow, eel-like enough to make people hesitate before naming it correctly. It moves with almost no wasted motion, no roar, no charge across the sand. Just a ribbon of muscle in tropical water, following fish where fish already feel safe. If you are in the water with one, you may not see a threat first. You may see a shape.
Then the shape moves. The official version is clinical, a family of highly adapted marine reptiles, a set of species that thrive in warm seas, a venomous hunter with specialized anatomy and a complicated relationship to land. The real version is harsher and stranger. A snake learned how to belong to the ocean, but it never fully stopped needing air. Number 3. The apex that earned the legend. Is the one fear movie cameras made famous, but the real animal is worse in a different way. On the coast of South Africa's False Bay, Alison Cock has been going back to the same water since 1999. More than 500 trips, same route, same light, same patient look across Seal Island, where roughly 60,000 Cape fur seals crowd the rock and the water around it. At dawn, the whole place changes. The seals begin to leave in groups. The light is still weak. The surface looks calm enough to trust. Then the sharks move in. They stay below the line of sight. They rise hard from the dark and hit from underneath, using the shape of a body built for that exact moment. Torpedo form, heavy muscle, fast acceleration, no wasted motion. Cock has watched that sequence over and over, not once, hundreds of times. Long enough for fear to stop looking cinematic and start looking like routine. That is what makes a great white shark so effective. It does not need mystery to be dangerous. It has a working schedule. A young shark stays closer to shore. An adult drifts farther out. The species changes with age, moving through temperate and subtropical seas instead of sitting in one haunted corner of the ocean. It shows up near seal rookeries. It also takes easy meals when it can, including whale carcasses. The animal is wide-ranging. It is not trapped in one image, one beach, or one movie poster. The body is built for a long life in a hard world. Great whites are born at about 4 feet long. They can grow to 21 feet. They can reach 4,500 pounds. They may live more than 70 years. Females do not mature until around 33 years old. Males until around 26. That is a slow life, a slow maturity, and a slow recovery if the numbers start falling. This shark does not get rescued by speed. It gets trapped by biology. A great white can spend decades becoming the predator that people fear in seconds. That mismatch is the whole story. The animal arrives late. It reproduces slowly. It cannot replace itself quickly. So when fishing gear takes one, or bycatch takes one, or pressure builds in a region where nobody is counting carefully enough, the loss is not brief. It lingers. That is the second story inside the legend. Not only predation, pressure. The shark became famous because Jaws gave it a face in 1975. The movie taught the world to fear a fin cutting the surface. But the real animal is not a script. It is a vulnerable apex predator in a changing ocean, protected in many places and still at risk in others. And the deeper the science goes, the stranger the pattern becomes. Some white shark populations seem to be increasing, including in parts of the Northwest Atlantic. Other regional populations remain heavily pressured, and some are still poorly measured. NOAA still has unanswered questions about abundance and movement. The ocean keeps the final draft to itself. So the shark stays where Alison Cock finds it best, below the seals, below the surface, below the moment when panic begins. You were there at dawn. The seals break apart and move offshore. The water looks empty. Then the line between safety and something else disappears in one upward burst of gray muscle and teeth. What comes up from below does not look like a monster. It looks like a predator that learned the oldest trick in the sea and never forgot it. The island goes quiet again. The seals regroup. The light gets stronger, and the shark is already gone, slipping back into the wider water where it can outlast the story people told about it. Number 2. The extinct giant everyone still measures against. Is the shark every modern predator gets compared with? Imagine standing on a Pliocene shoreline about 3.6 million years ago, with warm water in front of you and a shadow moving under it that is longer than a city bus. Megalodon is the problem. You never get the whole animal at once. You get teeth, huge, serrated, iron-colored teeth, sometimes 18 centimeters long, pulled out of marine rock like evidence from a crime scene. The rest was cartilage. Cartilage disappears, teeth stay. The species survives in museums and journals more than in flesh. The shark is usually classified as Ototus megalodon. It lived roughly from 20 million to 3.6 million years ago. That span is long enough to make entire coastlines come and go. Long enough for whale bodies to change, sea temperatures to shift, and oceans to redraw their food chains. Yet the predator itself is mostly gone from the record now because the record was always partial.
A jaw with 276 teeth leaves a trail. The skeleton does not. The numbers get ridiculous fast. A recent museum estimate puts the maximum length at 24.3 meters. That is not a big shark. That is a moving event. A 16-meter individual has been reconstructed with a head about 4.65 meters long, a dorsal fin around 1.62 meters high, and a tail nearly 3.85 meters tall. You are not looking at a creature that fits neatly into the category of large marine animal. You are looking at something built to turn other large animals into pieces. Its bite is part of the reason the name still lands like a threat. One megatooth shark dentition study used an estimated bite force of 49,051 newtons. That is the kind of force that does not merely puncture prey. It crushes through it, then keeps cutting. The jaws held hundreds of teeth, not a neat arcade of little needles, a conveyor of blades. Whales, large fish, other sharks. Anything heavy enough to matter in the water could end up in that mouth.
If you were a whale calf, a seal-sized burst of panic would not help you. The animal did not need to chase forever. It only needed one clean angle. Picture a curator in a museum drawer room in 2022, turning a fossil tooth under white light. The old story said Megalodon was simply enormous, fixed at a few familiar pop culture numbers. The new work keeps making it stranger, bigger. More recent estimates have pushed the size upward again. That matters because it shows the shark is still being remeasured, still being rebuilt from fragments, still refusing to sit still even after extinction. The science is not polishing a legend. It is chasing a body that vanished before humans ever had a chance to see it alive. Extinction is where the tension sits. The youngest reliable fossils put the end at about 3.6 million years ago, by the close of the Pliocene. By then, the oceans had cooled. Prey communities had changed. The world Megalodon had been built for was no longer the same world.
Maybe the food base shifted. Maybe other sharks took pressure where it had once ruled alone. Maybe climate did the damage slowly enough that the animal never got one clean final blow. The fossil record does not give a dramatic death scene, it gives absence. We know this shark mostly because the teeth were left behind. We know it vanished because the teeth stop appearing. Somewhere in between those two facts is an animal so successful that its disappearance had to be reconstructed from scattered clues on the seafloor and in rock. No body, no last swim, just a gap where the teeth should have kept coming. If you want to feel the scale of that gap, do it as a what if. You are in a modern ocean survey boat, and the sonar trace below you catches something broad and slow near the surface. At first it looks wrong, too large to be a single animal, too clean to be a wreck. Then the shape rolls, the mouth opens, rows of teeth flash in a line that seems to go on forever. Every modern predator in the sea gets compared against that image, because nothing alive today quite matches it. Great white, tiger shark, orca, they all get measured against the extinct giant everyone still uses as a standard. The comparison is useful, but it can also flatten the truth. Megalodon was not a movie monster. It was a real shark in real oceans, shaped by prey, temperature, and time. It succeeded for millions of years. Then it disappeared. The teeth remain in collections, in strata, in old seafloor deposits that only make sense after you know what you are looking at. The body is gone, but the evidence is hard. The largest known Megalodon tooth reaches 18 centimeters. The species is gone by 3.6 million years ago. The rest is built from teeth, estimates, and the silence left behind when a top predator slips out of the fossil record. Number 1. The deep that kills machines. Is the moment the ocean stopped being a myth and proved it could kill a nuclear submarine. On April 10, 1963, USS Thresher was about 220 miles east of Cape Cod, Massachusetts, on deep diving trials after a recent overhaul. She had been commissioned on August 3, 1961. She was the Navy's first nuclear-powered attack submarine of her class. The boat was meant to show what the future of undersea war could survive. It did not survive the morning. The record that matters starts as testimony and ends at a depth, a submarine under pressure, a routine test dive, a growing problem below the hull. The Navy later concluded that a probable piping failure let seawater into places it did not belong. Flooding followed. The reactor shut down.
Once the boat lost the ability to make buoyancy fast enough, the ocean had time to finish the job. On paper, that sequence sounds almost clinical. In the water, it was a trap closing. Thresher carried 129 people, 112 crew members, 17 civilian shipyard technicians. Every one of them was lost. There was no rescue on the bottom waiting for them, because the bottom was 8,400 feet down. That is not close to human hands. That is not a place where a diver can descend, fix the damage, and bring anyone home. That is the abyss with a specific latitude and longitude attached to it. You can read the number 8,400 feet and still not feel it. So imagine the boat there in real time. The hull deepens into silence. Systems begin to fail in sequence, one after another, because submarines do not die all at once. They lose options, they lose margins, they lose time. Then they lose the one thing that matters most, the ability to rise. The disaster did more than sink a ship. It exposed a chain of failure that the Navy could no longer treat as an assumption. Flooding, reactor shutdown, loss of blow capability. Together, under pressure, they made the submarine unrecoverable. That was the lesson written into the wreck. Not in theory, in steel. And Thresher was not just any hull. She was the lead ship of her class, the one everyone watched, the one meant to prove that deeper, quieter, faster submarines could also be safer. Instead, she became the reason safety had to be rebuilt from the inside out. After the loss, the Navy created SubSafe. Every weld, every valve, every pipe, every system that had to work when the water got in. The program did not come from optimism. It came from 129 names that never came back. The wreck itself stayed where the sea put it. In darkness, no searchlight reaches. No immediate human rescue. No last-minute surface miracle. Just a submarine settled into the deep, and a hard fact that could not be argued away. Machines built for the ocean can be killed by the ocean. That is what makes Thresher different from the monsters people imagine beneath the waves. There was no jaw, no tentacle, no legend rising from the black. There was a ship, a test, a failure, and a depth that swallowed the evidence. The terror was not hiding in the water. It was built into the pressure, into the plumbing, into the tiny margin between functioning and unrecoverable. The public memory of the loss has never settled fully on one clean cause, because the initiating failure was never seen in the way a camera sees a strike. The Navy's inquiry pointed to a probable piping failure, but the exact chain from that first failure to total loss remains something people still argue over. What is not in doubt is the outcome. Thresher went down. All hands were lost. The sea kept the submarine and returned only the lesson. And that lesson was brutal in its simplicity. If you design for depth, depth gets a vote. If you assume redundancy without proving it, the ocean will take that assumption apart. If a system fails where recovery depends on seconds and pressure and perfect timing, there may be no second chance at all. So the final image is not a creature. It is a submarine in the dark, losing buoyancy faster than anyone can save it, with 8,400 feet of water above the hull and no way back to the surface. The myth of the deep used to be about what might be down there. Thresher made the truth colder than that. The deep does not need a monster. It can kill machines, crews, and the idea that distance means safety.